So our next and final speaker is Hugo Herbelin, who will talk to us about the construction of simplicial and cubical sets in indexed form, and more specifically about the case of degeneracy.
Okay. So maybe using the scale of Ambrouche at the beginning of the afternoon, so between syntactic and semantic. This is let's say I consider it more as a syntactic approach, but and I don't know exactly how to fit also the talk, because it will talk about things which are somehow 10 years old, so that some people knows already quite well, but maybe other people don't know them very well. But at least I want to emphasize 4 points. Moves here. So usually we consider, so 10 years ago, there was a problem of semi-simplicial types. And I believe at the beginning, there were a confusion in the problem of semi-simplicial types, that there were two problems at once. One to define semi-simplicial sets for types, but another problem, which was to define semi-simplicial sets in a form which I would call in the index form, in the sense that a usual presheaf can be seen as a presheaf in a fibered form, which is a bit counterintuitive, because usually in category theory, we have the presheaves on the index side, on the fibration on the fibered side, but we can look at the presheaves which are at the index side in the general view, but we can see them also as fibers, because we have maps from sets to sets, and then goes one level more on the index side, and have what we call semi-simplicial types, but removing types by sets. So which is an indexed way to present presheaves. So this work is about an indexed way to present presheaves. So somehow the index fiber correspondence is considered sometimes as an anecdotal way of representing things. But when we have a hierarchy of such fiber index correspondence, we have an iteration of it, and it starts to be a bit less simple than when we have just one index fiber correspondence. So this is somehow what the talk is about. And this is the first line about the talk. The second point of the talk is that there were an observation at some times from several people, apparently, I don't know how much it's now folklore, that when you look at simplicial sets and cubical sets from the parametricity point of view, you observe that they are the same. It's just a question of arity, of whether you take predicates or relation or families or correspondence. If you have in the unary case, you obtain augmented semi-simplicial sets. If you are in the binary case, you obtain cubical sets. So how much can we say about both simplicial sets and cubical sets by looking at them in the same framework? And this is what we are doing here. We are following parametricity. So we just have to generically consider unary or binary parametricity, and we are telling things which are both for augmented semi-simplicial sets and cubical sets. The third point on outcome of this work is an observation that, contrarily of what we might think at first, that degeneracies in simplicial sets are the same as degeneracies in cubical sets. No, that's not true. Actually, the degeneracies of simplicial sets are the unary case of the connections, which was a bit surprising at first. I don't know if this has already been observed or not, but it's a new observation. Another point of the work is that this is fully formalized in the new software called Rock. Okay. So Torsten like to call it the fiber index correspondence for dummy, for the dummies. So here it's a version just for H set, which is just either you take a fiber, fibered representation or a dependent representation. So you can prove this to be equivalent. Usually one says that it's equivalent using the univalent axioms. But if you know that univalent is about defining somehow equality, so if in the definition of equivalent here, we are extensional enough, meaning that every time we compare function, we compare them pointwise. Every time we compare types, we replace the equality by an equivalent again, then actually this is provable even without univalence. As a side remark. Okay, so the fibered, so then what I called presheaves in fibered form, so what people call presheaves in general, is a presentation like this, for instance, for cubical sets, with a family of sets with maps. It's even here semi-cubical sets in this case. On the index form is you apply stepwise at each level, you apply some form of fibered index correspondence, and then you replace this by a family of families, each family is depending on the previous one. So this makes a highly dependent structure. So it cannot be presented anymore as a function from natural number to sets, but as a streams, infinite streams, because of the dependency. We will see that later. So in the review for the proposal of the talk, there was the question: how does it? Are we sure that this represents the same thing as that? And I fully agree. There is apparently space for research here. Can we develop a meta theory or a theory of presheaves in index form? I believe it's worth to do it. So intuitively, we can go from the fibered form to the index form just by iterating the fibered index correspondence. We have so when we do the work back and forth, we don't arrive to the same presheaves. Of course, here we arrived, for instance, to a ready fibrant presheave, but there is we can think there is an equivalence. And, one day it should be interesting, I believe, to prove it formally, but that's not the purpose of the talk. So I'm not completely of categorical theory culture, but this kind of sets on which depend each family of the family here are formulation of what apparently is called a matching object. So then here in this example, I show how to go from one side to the other using this kind of machine object associated to a presheave Y, but we can define them directly without mentioning at all the notion of fiber presheave, and we can define index presheaves directly. At least we have instances of it. For instance, there were one already in 2012 by Bobotsky and other by this author. And I made one also, this is why I'm saying it's 10 years old, even 12 years old. I made one 12 years ago, and a new one to be now published based on the parametricity rule. Why to do that? Why to use this kind of presentation? So, so this is why I was mentioning the talk of Ambrouche. There is a distance between the syntax and eventually semantics. So there is obviously a distance when you take type theory, which has dependent type, and you have presheaf models where the fiber style. Can we reduce this distance? Can we preserve more of the strictness, more of the definitional rules by having models which are closer to the syntax? And the hope is that this parametricity-based presentation of presheafs in index form are closer to the syntax and will preserve more definitional rules than the ordinary models, especially, for instance, for the universe. But that's not also the purpose of this talk. Okay. Then I don't know how much it's common to present semi-simplicial, augmented semi-simplicial sets and cubical sets the same way, just as a string, as words over an alphabet of n plus 1 letters. So you have an alphabet, say mu, and you define the morphism as sequence of letters on this alphabet extended with an extra letter star. So you define a composition like that. And depending on the arity of star, if it's a singleton element, you get some augmented semi-simplicial sets. And if you take a two-element set, you have semi-cubical sets. How much do you feel familiar with that? No, not really. Except if you don't suspect. So, for instance, each time you select a letter, you're selecting a face. For instance, for the standard simplices, with this notation, the top simplex is just only star. So it's augmented semi-simplicial sets. So it means there is a shift by 1 compared to semi-simplicial sets. So this means you represent dimension 2 of semi-simplicial sets by dimension 3 of augmented semi-simplicial sets. Or conversely, you can start from -1 so that it fits the usual. But in terms of length of the alphabet, you have 3 letters to represent dimension 2 of semi-simplicial sets. And yes, so the main simplex is only star, and then you can take faces by selecting so here you select the third face, the first face, the second face, and then you select the second time faces, and it's augmented semi-simplicial face. So there is an implicit point hidden in the picture, which is 0, 0, 0, which is everyone is connected to it, but geometrically we are not used to represent it. Or if you want to represent it, you have to imagine this as the point is under the sea as an iceberg, and you see just the top of the iceberg, which is the dimension 2 of an augmented semi-simplicial types, dimension 3. Okay, anyway, so this is a description of a common description of augmented semi-simplicial and semi-cubical. And then, yes, the talk was about adding degeneracy. So we made a formalization we completed the formalization of this part without degeneracies and generically for semi-simplicial and semi-cubical 2 years ago, maybe. And now we added the degeneracies. So we added only one degeneracies in the last direction because it's simpler. But then you can add permutation. There is a recipe also to add permutation, and you will get the other degeneracies. So what it means to add the degeneracies? The index structure is a stream of x0, x1, x2, which are families. And what you have to add? You add a reflexivity from the set x0 to the set x1. And the reflexivity in the cubical case, this is the cubical case, is connecting twice x0. And so on. So you have a lot of dependencies, but you can see that R2 basically up to some tube, some surroundings, up to the dependency of an element in X1, which are points, you can build an element in X2 which connect X1 and which connect X1 to itself. This could be done easily if we had a way. So this part, this dependency is like a matching object. If we were able to move a matching object for X1 here to a matching object to R2 in the correct way, then we would be able to do the job, and we can do it. First, before doing this construction, my remark on connection and degeneracies. The difference I'm making here is that degeneracy. So then I will use now different terminology, because degeneracies, as I said, does not mean the same as the semi-simplicial and the semi-cubical with respect to this view of seeing things. So connection will involve two directions, and reflexivity involve only one direction. So a reflexivity will connect, will move one level, a point here, a point. No, sorry, it will move. Sorry, a line here to a square, just by duplicating these lines and connecting it. So we have twice the lines, and we connect it on the side by two reflexivity. On the other side, the connection involves two directions which are different. So if we want to move to lift a line x1 in a square, we move it in two directions, and we complete the extra data with the reflexivity. So then when we degenerate the connection to the unary case, what we have is a lift from the dimension 0, which is the dimension of points for semi-simplicial types, to here for this case, sorry, x0 to a line connecting between 2 points, but these 2 points in the semi-simplicial case lives in two different directions. So this is what in which sense I'm saying that the degeneracies of this is the degeneracies of semi-simplicial are just the connection move where you move from the two to the dimensions to the RT2 to the RT1. How much time do I have? 5 minutes. So on these reflexivities, what are the reflexivities then in the simplicial case? Sorry, these are the same as the one we can find in parametric type theory, which are different from bottlenecks. So then now I will enter, if you have the courage, into a more formal part. How this construction, how this thing here is presented. So it's made so it's an intermediate level. It's not rock code, but informal. It remains informal. So as I said, this first we collect the x0, x1, x2 into a stream. I don't know how much it's standard because I already presented this some years ago already, so maybe some of you know, or maybe I can redo. So we make a stream. And this stream is dependent. So each new element of the stream, each xi is dependent of the previous one. So we need a data structure to represent the x0 to xi minus 1. So this definition. This definition is a truncated new set. By new set, we mean either semi-simplicial or cubical. So we collect a truncated new set, which is a collection of x0, x1, x2. And then we can take the limit, the co-inductive limit, using this definition, which is initialized with an empty sequence of x0, on which we add the x0, we add it to, there is a parameter, we add it to the parameter of the co-inductive type, so that we can go on up to the infinity. The key is to define this, each predicate, we will give it a type, which is dependent on the previous x. So the type of xn will be dependent of the previous x, on how to define this. And we will use as recipe a decomposition of here cubes in dimension n as piles, as in layers. We call them layers. The first layer is cubes in dimension dimension n minus 1. Then we complete with a line which is stretched to fill, because what we need is to complete this on the inside. So we take a line which is stretched, and then it remains to cover, and the cover is just a cube of dimension 0 that we stretch. So basically, at the end, it gives a definition with 3 components: the frame, the layer which compose the frame, and each layer is made of, in the cube, of 2 paintings. The paintings themselves recursively are recursively made. So the structure has this form, but I think it starts to be very complicated. So we have a notion of restriction of frame, and it goes to all the structure. And we need a property of coherence of frame. So this is very familiar and I don't go into the details. And to add degeneracies, we just need, given one stream of x0, x1, we can define a new stream, the stream of reflexivity from R minus. So here I made it in the case of augmented semi-simplicial. This is why there is a minus 1. There is a stream of reflexivity, which themselves are dependent. The second level depend on the first, the second level depend on the two, and so on and so on. We have 2 degeneracies to prove, and it works. Roch accepted it. Okay, summary. So machine check construction of presheaves in index form, non-standard way of defining presheaves. We're using iterative parametricity so that we hope eventually to have models closer to the syntax and with better definitional properties. Doing at the same time semi-simplicial and cubical, but there are a lot of to do. We can do permutation, connection, pi types, sigma types, universe. And we also, so our first formalization use a lot of equations. So I would not call it transport L, or maybe we are so used to the L that we don't notice it as a L anymore. But we use a lot of rewriting, and we have a new version, probably also, which use more of the meta language substitution, let's say, which is much more compact, but not yet finished. Okay.
For the degeneracy, you don't need any equations. Like you don't need to say things like degeneracy at one level, how it relates to higher degeneracy. It's all in the index of degeneracy.
Yeah, I was just wondering, this co-inductive construction, is this related to the idea? I mean, you can always look at inverse categories with the finite, the index by finite height, and then you can always shift them by one, and this way you can construct all the elements of this index type. I mean, it's not about degeneracy, it's just for semi-simplicial or semi-cubical. Okay.
Okay, I have a question. So you explained that one-dimensional parametricity is simplicial sets or semi-simplicial sets. Two-dimensional is cubical sets. What is three-dimensional parametricity then?
It's not very intuitive. We can try to make someone in the room trying to make sense of it. So let's say it's like a cube with you have different view at it. Like a cube where you put a line in the middle, like it makes a square with nine nodes, or you can put two lines on the top and one on the bottom. And actually, you can put three lines on the top and zero on the bottom. It's difficult to have intuition about it.
Sounds complicated. Any more questions? Okay, then I have another question. So in your formalization, you just have one degeneracy instead. Does the same method generalize nicely to more degeneracies and connections?
So we didn't make permutation, except I made some notes, but it's possible. But the advantage of one degeneracy in the last dimension, it's very, since we are building the matching object by layer, it's very easy because you just have to lift a restriction of a matching object to the one in the level higher, in the dimension higher, but which have exactly the same structure. Otherwise, if you have permutation, you have to think at more. You have to manipulate two layers at the same time because you have to cross layer have to cross. It's a bit intuitive, but this one is simpler to do.
It would need a bit more work to get the.
No, it's more work. I mean, obviously, every time we add a new construction, we have to unroll the definition with frame, layer, painting, restriction of frame, layer, painting, and coherence. But once you do that, it works. It's quite methodical. It's in this sense also. I'm saying that we should arrive to some meta theory of this, so that we don't have to redo all the steps every time we introduce a new construction. There is something generic to find.
Thank you.
But I expect that at some point, if you add connections or more degeneracies, then you cannot be fully indexed anymore. You will have some equations on top. Isn't that the case? Like if your category is really arbitrary, then don't you need equations at some point?
You mean arbitrary? Any ready category, axiomatically defined. I don't know. In our case, no.
comment on that. So I think you get the index fiber correspondence for that for direct locally finite categories. So that's, I mean, a direct category is half of a reading category. That's where you can like read off more or less a kind of a type signature that gives you the structure. But for a full, yeah, if it's not a direct category, if it's not a question, the comment, but maybe it's not yet.
Any more questions?
Yeah, I do have a little follow-up on that thing with equations, which is that in if you have a really well-behaved reedy category, like an easy category, Eilenberg-Zilber, then you do get that every degenerate object is generated from a unique non-degenerate object, but even in that case, you still don't get that it's generated by a unique path of elementary degeneracies. So I do think you would need equations at some point for some of these categories.
I don't know.
Sounds like a good plan for future work. Okay, so let's thank the speaker once again.